So the folks in Zoom land, just have your cameras off if you don't want to be on camera. On the screen here is a bit.ly link to the R script for all of the material today. So I have a sample. I'll put this in the chat here. So the R script is there. And then I do have like a sample data set for just a little demonstration of running models over, why the fuck is this? I shouldn't swear when I'm recording the thing. There we go.
This is your workshop, do whatever you want.
Yeah. That's like the best. That's like if Tom Morello was giving advice to people. Okay, so the outline for the workshop today is we're gonna go. I'm gonna start with loops because that's sort of the most basic thing. There are different ways to do loops, but we're gonna focus on doing 4 loops today. So like not like number 4, but for this. And then I'm not really going to talk about mapping, which is like how the per package applies loops or implements loops. I'm going to talk a little bit about the apply family of functions, which are similar to loops, but just a little bit faster, a little bit easier to write, but a bit more tricky. So most people start programming using loops. So we'll start there also. And then I'll talk about functions for a little bit, and then we'll combine them and I'll show just some different applications for these things. So the idea is that this is going to be like a basic introduction to programming in R. And the reason why we program is, it's a little bit of a headache at first because you have to write the script. But if anytime you're doing something repetitively, writing something that automates a repetitive task not only reduces the amount of time you spend writing code, but it also reduces the probability of making errors when you're doing like Mad Libs coding, I call it, where you're just copying the same statement and changing 1 or 2 things. There might be a typo there, and usually like the program just stops, but sometimes like it'll keep going. And you're like, why is this thing continuing to go? And it's like you've made a typo that created this gigantic matrix that R is now trying to process. So loops just allow you to repeat the same action over and over again. Functions are similar in that they're a generic command or set of commands that you can apply to different situations. And so when you run the lm command, like you can actually look at the code and you can see what it's doing. And so we'll talk a little bit about that, but again, loops are sort of where things start. Then the other thing that I'll just mention off the top is, especially when you're starting, program your loops and functions using base R, because tidyverse will cause problems because of how its conventions. Base R refers to objects directly, either like a specific object, a vector, a data frame, a matrix, an array, that sort of thing, or a list. Because everything in the tidyverse starts with a data frame and then picks a column. In order to do programming in using tidyverse conventions, we have to use something called non-standard evaluation. And so this involves using special operators to declare all, objects or names. Most commonly, this double exclamation mark followed by SYM and then parentheses, right? And this is literally called the bang bang operator, right? Because an exclamation mark is 1 bang. And then, I mean, there are uses for like single bang and triple bang, but usually it's the bang bang and then symbol that we use. And then colon and equals is sort of what tells it to take whatever you've declared in the bang bang statement and then feed it into an equation, as opposed to using the equal sign on its own without the preceding colon, which is a declarative statement. If that's difficult to understand, program in base. And so again, just to start with the basics, right? Loops and functions work off of lists. And the idea is we take a list as an input usually. So, the apply functions can take other things as an input. Sometimes we can take columns as an input or a vector, but some sort of like enumerated object is the input, right? And we work with those items in the same way that we work with columns and data frames through the subset operator, right? The $ operator is a subset or a selection operator, but it only works on named things, right? So in a data frame, all of the columns are named. And so we can use the $ selection operator. In a list, the items may or may not be named. If they're named, then you can use the $ operator. But because, again, these things are meant to be generalized, we usually use the square bracket selection operator, right? And in this case, it's almost always the double square bracket, not the single square bracket. And there's not enough time to explain the difference between them right now. So just almost always the double square bracket. And then anything that can be programmed as a for loop can be programmed as something of the apply family or the map family from tidyverse. I show a little bit of that at the end, but we're just not going to cover that because getting through loops is enough. You can have loops within loops. And this is where it's like, well, if you can do everything with, like if apply and for are generally interchangeable, why the hell would we use one over the other? Well, apply is just quicker to write. It also tends to be faster. And so once you get into more complex programming, if you're nesting loops within loops within loops, it's generally best to stagger them, where you apply a loop, for example, right? Or you loop and apply, as opposed to applying and apply or looping a loop. And the basic structure of a loop is similar. And I tell this to folks when they're doing quantitative methods, is you need to learn how to read and put code into words in the same way that you need to learn how to read and put equations into words, right? And so all loops have the same structure, right? You designate the output object, you declare the iteration variable and how many iterations you want, write an individual instance of the command you want to run, but in a generalized way that uses variables rather than specific object names, and then you profit. Bonus points to anyone who gets that reference. And then the output of loops and functions can be collapsed using this handy command called do call. You don't need to understand how it exactly works, other than you will often be do call rbind or do call cbind, since the output of a loop is usually a list. So yeah, Caleb.
Just quickly, like I see that not do call, but call in general is when there's like a regression output, it says like call top. What does that mean?
It's calling a function.
Okay.
That's what it is, right? And so when you use the do call function, it literally reads like, so do the function that I'm about to name over everything in the object that follows. So that's how you read that statement, right? And we're going to start with a statement here. So we'll get right to reading it. So for the folks who just entered in Zoom land, look at the chat. There's a link there to a public Dropbox where you can download this R script if you want to follow along there instead of my shared screen. So we'll work with some generated data, and this is actually a great case for using a loop, because I'm generating 9 random variables that are uniformly distributed between 1 and 6 inclusive, with n equals 500, right? So I could write these commands, right? But I mean, this is stupid. Like most of this is exactly the same. The only thing that changes is this, right? So this gives us a clue. Everything from the equal sign onward is going to be the same. The only thing that changes is x1, x2, x3, x4. So we're going to declare variables for these things that we're creating. And then we can just loop this over some sequence that ranges from 1 to 9 inclusive, right? So When we're programming a loop, remember I said we start with identifying or creating the object which we're going to dump our output into. This is another advantage of apply. You don't need to do that, but anytime you write a loop, you need an object ready to accept the output, right? And so here, we just create a blank object. I'm going to call it dat2 because our first one was dat1. And I'm just going to loop the statement above, right? And you see the looped statement is exactly the same as all of my specific statements up there, but we've replaced, x1, x2, all the way to x9 with dat2, which is our destination data frame, and then double square brackets I, right? And so how we would read this is for every I in the sequence 1 to 9, create a uniform distribution of n equals 500 with minimum of 1, maximum of 6, round it to the nearest whole integer, and dump that into dat2 sub I, right? So dump it, take this thing that I'm doing and dump it into slot I of the object dat2, and it'll automatically turn it into a list. Yeah.
And I is like the observation.
No, I is just, I could have called it J.
Okay.
I could have called it X. A lot of people start with X. I like I because in my mind, it's like iterate.
It's where you are in that 1 to 9.
I believe call it the same thing.
Whatever.
Yeah.
Yeah. I think that's what-
Yeah,
Everyone
yeah.
knows the eyes, yeah.
Yeah, that's what we had in our
Yeah.
class last semester.
Right, but I
Hey,
mean,
John,
I could
John.
literally like
John, can you share
for
this?
every
John, can you share the script
you know,
screen
like-
so you can see it?
cat,
Wherever we can.
I love kids.
right?
That's nice. I love you too.
Right? So it's, for every cat in range 1 to 9, output to dat2 sub cat, a uniform distribution of n equals 500 with minimum 1 and maximum 6, right? So you can, I like I because in my mind it says iterate. And then as you get into like nested functions, right? You might start with I, then go to J, then go to K, L, M, that sort of thing, right? So yeah, you'll develop your own conventions. And then we're not going to get into while loops, which are quite complex, but those almost always require like 2 declared variables. So you'll have like an I and a J. Anyway, so the output of a loop is usually a list. And so let's just take a look at what this thing we've created is, right? So it's called dat2, and what is it? Oh, look at that. That's a lot of numbers going on, right? And so each one is of length 500, and it's just 5, 2, 2, right? So it's that uniform distribution that we've created. And so what we really want is the first thing that we created, dat, which is a data frame, right? And so I could create a data frame by binding all of the columns or binding all of these objects together into columns, right? So cbind is bind into columns, everything that's, I tell you to bind and output it to an object, right? But that's kind of lame, right? Like this, this works, but this is lame. This works, but it's not efficient, right? Like why write 9 lines when you can write 1 line? So this is what the do call command is, right? It's that we're doing the same thing to all of these things, right? So do call is literally do this function that I'm about to tell you to do and do it to everything in the object that follows. So that's what this is, right? So if we run that, dat2 is now has been bound together, right? And you can see they produce the exact same results. Now, the thing with using do call is when you bind vectors together, it creates a matrix or an array, and we actually want a data frame. So we need to just coerce it into a data frame, right? So will assign the object dat2 and say, coerce it into a data frame and assign it to the object dat2. And you'll see that now the class of the object is a data frame. So that basically that's what you're trying to do. So another application of loops. Well, actually, I guess let's take a second to pause there. Like, are there any questions? Oh, there's some questions in Zoomland. Oh shit. Fuck. Hey, can you guys see the script now? Or alternatively, have you downloaded the script? Okay, perfect. Sorry, really sorry about that, guys. If you just arrived in, like, oh, I'm muted. That's why I can. If you were okay, I'm just fucking boomer moment here. Okay, we're good. Sorry. So any questions about this here? You'll see some more examples here in a moment, right? So that's, I mean, not a lot of people generate data, but I had to generate something for this workshop, and so I thought this is a good case for that, right? So another repetitive task that we do is we have to transform data, right? Now these days there's better ways to do this. Like if you look at the labeled package and the SJ labeled extension built by a prolific package developer, Daniel Ludke, it will actually take any like SPSS or Stata data set that has labels. And there's a bunch of utilities there that allow you to just factorize everything using the labels. But for an older data set that doesn't have those things, this can be useful. But again, pedagogical purposes. And there's other transformations that you might want to do. So this is still quite useful, right? But if we wanted to recode stuff, right? Like back in the old days before tidyverse, right? This is literally what we had to do. So this is what, like to create a Likert item out of one variable. This is what, 1, 2, 3, 4, 5, 10, 11 lines of code, right? You don't want to write that over and over again. Even if you are, case when in tidyverse still requires, 5 or 6 lines of code. Car recode does this in 1. But then you'd have to program using a function and that can get messy. So yeah, I often just I literally have a function called make Likert because I can just loop it. So so here we'll write this code out once to create to turn our numeric variables that we just created into Likert type items and just loop it, right? So here our original data frame is dat2. And so I'm just going to make a new data frame called dat2a, just so we don't overwrite our original data frame. That's always good practice. And I literally just took this, and as with the function above, I replace every $sign and then x1, right? Because that's the first column in the data set. With double square bracket I, right? So generally $sign and then everything after it can be exchanged with double square brackets containing everything that was once after the $sign, right? Single brackets, like, we use this here as a conditional statement. So this is like vectorizing something over every element within it. Again, just don't think about that too much. Almost always, if you're making loops and functions, you're using a double bracket as a selection operator, right? And so, yeah, so all this is doing, right? So here it's like we're working only with with column x1 of data frame dat, and when it is 1, it gets changed to strongly disagree.
John, can you ask the Zoom people if they can see your? Because Tyler Romaldi sent me a message saying you can just see your desktop.
Hey, can you guys see this?
Probably because I didn't.
Yeah,
Okay, thanks.
Oh, so they're good now?
Actually, what I'm going to do, I'm going to stop screen sharing for a second because I'm actually just going to share our studio so that, yeah, okay,
Then it won't go away.
then it won't go away. Perfect. Okay, so, yeah, so here, I mean, it's just, when x equals 1, turn it into, when x1 equals 1, turn it into strongly disagree. When x equals 2, turn it into somewhat disagree, so forth and so on, right? And then at the end, we take this thing that we've transformed and we turn it into a factor with these levels. Yeah.
So John, did I get that right? So you're doing that for every variable in the data set, you're essentially converting it into like.
Well, yes, but this is only working with the variable x1, right? Because if we look at our original data set, right, we have these 9 variables and
Yeah.
Yeah.
So if you have a set of variables that you want to convert, you can just, okay.
yeah, so if we wanted to do that, we would have to repeat these 11 lines of code 9 times, which is stupid. So what this is doing here is, okay, well, I generalized, this specific instance up here, and then we've replaced the specific references to the column x1 to item I, right? So for every I in however many number of columns that 2A has, right? Because it has 9 columns, right? Do these commands, right? So on iteration 1, I becomes 1, right? So we do all of this to column 1. Next iteration, I becomes 2. We do all of this to item 2. Then it becomes 3, and then so forth and so on. And so, here I specifically said 1 to 9. I mean, I could have put like for I in 1 to 9, but using it as like n call dat2 just says, well, do it for however many columns there are in dat2, right? So
you would need a specific data set though, first that only has those variables, right? That you want to essentially.
yeah, so I mean, here it's like, well, but your data set has several different variables. Well, yeah, I mean, you can pull all of the Likert variables that you want,
Yep.
and then run this over and over again, right? And actually, when I get to functions, I turn this into a function called make Likert. So then you can loop the function. So you really only have to write this once, right? Another way you could do this, like let's say you have like the CES, which has like hundreds of columns, right? You could create a vector called, Likert vars, right? So you could do something like Likert vars, and you can just create a vector that, let's say you have these variables are in slot numbers like, 50 to 60, and then from 75 to 95, right? And then from here, you have, these are the column numbers for each variable. You can either use this as your for I in however this, or probably the better thing to do would be to temporarily create a new data frame with just these variables and then loop over that. So, that's sort of how I would do that. Anyway, so that's that, right? Another common one, creating summary statistics. So let's say you want to graph the univariate frequency distribution of all of these variables, right? We could loop this. So again, following the same convention, program one instance of the thing that you want to iterate. So here, we're going to make a table of variable 1, and then we'll turn it into a proportions table, and then I'll output it to an object called test out, and then we'll display test out, right? So there's the univariate frequency distribution. If you're following along with the R script, your numbers are going to be different because this is all random number generator stuff. So, so if they're different, don't worry about that, right? And again, here, this is a table, which is a special class of R object. So you probably want it as a data frame. And so we just have to coerce it into a data frame. So how would we generalize this? What does $ V1 become? Right, double bracket I, right? Or double bracket cat, whatever you want, right? So here I just said, I'm going to create another object that's empty, right? Null. The object's called myfrex. And then for every I, in 1 to however number of columns our input data frame has, I'm going to run the following function. And we're going to assign to myfrex sub I everything after this assignment operator, which is calculate the univariate frequency of data to a sub I, and then turn it into a proportions table, and then turn it into a data frame, right? So, I've chained together multiple things here using the pipe operator. So if we run this, we'll see now we have 9 univariate frequency distributions, right? And you could open this up as well, and you'll see it there. Oh, sorry, I realized I didn't actually run this. Let's run this again. There we go. We should be having the labels. I mean, incidentally, if you do use like the labeled and SJ labeled packages, you could loop the 2-factor command, and it would do the same thing, right? So it doesn't, eliminate the usefulness of loops, right? And then another example here, like we often have to create many plots, and so creating one plot is like, yeah, we could, write 9 of these ggplot statements, right? And so you can see here, myfrex is a list, right? And so I've identified the first data frame in that list using the square brackets, the numerical selection operator, as opposed to the name selection operator of the $. And I just run this ggplot command. But like, why would I do that? When, again, we can generalize this specific instance and then loop it using a for loop, right? And so there's different ways you can do this. You almost always want to assign your plots to an object, because then it's just easier to do stuff. And then, especially once you get into like survey data analysis and you're running any kind of MLE based model, and then you calculate average marginal effects, it can take time to calculate those effects. So a good convention there is calculate your effects first and then generate your plots. Again, use these intermediate objects because it'll make life a lot easier. So yeah, so again, like we just, for I and however many of columns there are in DAT2A, right? Do all of these things, make this ggplot command. And, it's a bit longer because I added like, standardizing all of the scales, making them into percentages, adding titles, and then setting the theme. And you can see, you can use the paste command, and that will paste the column names. Again, the ith column name from DAT2A, which is the name of the variable, right? And so now you don't need to have to worry about changing all of the labels for that. We've literally, also automated like the naming of each of the plots that we provide. So if I run this and print out all of the plots, you can see, right? The label there has changed, the title has changed, and we have all of that, right? It's same thing if we wanted to add a geom text command to add labels to that, like we can do all of these things too. And like this isn't to say that Stata and SPSS or even Excel can't also automate things, but like graphing in Stata is a friggin' nightmare. Like even people who stick with Stata because that's what they learned, will, many of them now output to R because just scripting is so much more efficient in R. So I'm not really gonna go through this. This is doing everything we did above in a tidyverse framework. Really, this is just to show you that the statements look different. And so we have to just be cautious about this, right? I actually fixed this here. Oh yeah, so if we loop the above and ignore the quasi quotation shit that we have to do with tidyverse, you get this weird result, right? So this is the first one, and look at the variable name. It's dat to a double bracket I variable. The second table is different, and if we compare these to our original frequency distributions, they'll match, but the names have gotten messed up, right? So this is why we have to solve this using quasi quotation and non-standard evaluation, right? So we have to say, okay, I'm not telling you to use this to use this as text. I'm telling you to use this as an object reference, which is why we have the bang bang operator in there. And then now if we do this, we'll see that we have the proper names there, and the values are unchanged. So again, I'm not going to spend time on that, but programming with tidyverse stuff can be annoying. And here again, we have to use symbol, the bang bang symbol command, and otherwise it's not going to work. I just lost it. So here, yeah, X equals, again, saying it's referring to this, not text that says dat to a double bracket I. Because if we don't do that, it just blows up. Oh, it actually ran. But you'll see, it's just everything is just one thing, right? So doing it for the calculation command sometimes blows up. So yeah, that's that. Any questions? Yeah.
So if we put it all into a function in the part where you say one column, and column, can you automate it to put the name of whatever column you want?
Sure.
Okay,
Yeah.
you can do that function.
Yeah, I mean, like there's sort of I guess one of the places where I got started with this is, you can make vectors that contain all sorts of, useful items in R, right? Like you can make a vector of hex values for colors, and you could call it something palette, right? And then when you go to your scale fill discrete command or scale fill manual, instead of, C and then writing out the vector, just plop in the vector that you made, right? So it's the same idea here, is we're, we're just referring to something we've already created. So again, I'm not gonna spend too much time on the apply stuff, but generally everything above that we did using a for loop can be written using one of the variants of the apply function, right? And there's vanilla apply, L apply, S apply, M apply, and T apply. And the syntax is all different for them. It's annoying, but you do it enough, you get used to it. Like Hadley and co. Wrote the PURR package, which has the map functions, which are standardized versions. So, I never learned those because I got comfortable with this, but starting from scratch, it might actually be easier to spend some time with PUR and learn those because they're more consistent, right? And so we might read a for loop as, yeah, for every element X in input, do the following function. We read the apply statement as apply over this input, the function below using the variable X, and then the function follows. Right? Lapply is basically the same as for. It takes, a list amongst other things as an input, but it always returns a list. Sapply, again, takes a similar set of inputs as lapply, but it returns a vector or a matrix, right? Or a data frame, or something you can coerce into a data frame. Vanilla apply takes a data frame or matrix as input, and then returns a list, vector, or array, depending on what you tell it to do. This was heavily used before dplyr was developed, because now dplyr just has group by and summarize, which does row-wise operations, and apply was commonly used for that. But it's still quite useful. Like if you're working with survey data, you could take like a weighted mean by applying the weighted mean function, and it's a lot faster than using the survey package, for example. Mapply is like lapply, but with multiple inputs. And then tapply is like apply, but it breaks up a data frame into groups before applying the function, right? So whereas, apply was basically supplanted by summarize, tapply was supplanted by group by and then summarize. And again, here are just examples. So this is how we did our for loop above, but if we wanted to do it as an lapply, again, you see, so outputting to this object, we're going to lapply from 1 to however many columns that 2A has the following function. Then I define the function, and then I close it off. One common place where people get, and again, I'm not spending too much time on this, but just where people get messed up when they're moving between for and apply is for is written like for, like I in 1 to, 9, some function here. Lapply is lapply 1 to 9, some function, and then you close off the bracket, right? So in a for loop, everything in curly braces, the function, comes after the closing parenthesis. And in lapply, the function, including the actual, like the function definition within the curly braces, happens before the closing parenthesis. You're gonna be like, why are you hammering that point? It's like, you're gonna fuck it up. Like, it's just, if it doesn't run or it's running weirdly, it's because you might have put ordered the curly brace and the closed parenthesis, improperly. So just watch out for that, right? But anyway, so this is the lapply version. You can see it produces the same result. And actually, what I would probably do here is the sapply, because it automatically coerces everything into a data frame anyway, so it's a bit more expedited. But again, that sort of requires you sort of knowing that. And then using apply, it's a bit different, apply, because you can see I don't actually use the selection operator, because apply always takes like some data frame or matrix or array and applies either over rows or functions. So you don't need the selection operator anymore. You just need whatever variable you've declared for your iterations. So 2 is the margin. So if you look at the apply function, the conventions, it's apply to some object X along which margin the following function. The margins are declared using matrix notation. So if you select margin 1, that's rows. If you select margin 2, that's columns, right? Same thing with the old school way of doing a crosstab, where you would do like a table like dat x1 dat x2, you know, if you outputted this to a proportions table, it's going to calculate table-wise proportions, right? Like, look how small the proportions are. If you set margin equals 1, you get row-wise proportions. If you set margin 2, you get column-wise proportions. So yeah, so margin 2, just, you know, this says, actually, I should probably put margin equals 2. Do it over the columns. And you can actually do it over rows and columns. But then like the behavior gets really unpredictable there. Like, so there's the rows.
Oh, I thought you meant like you could do like C.
Oh yeah, you can do C1, 2. But like this function wouldn't work for that,
Yeah,
right?
Yeah.
So something like, I'm going to do this in a new structure so it doesn't fuck up my object. So something like, you know, if you did it over 1, yeah, it's just, it doesn't work, right? We could do, let's maybe sum. We'll do this over our first data frame because those are all numerics. So it doesn't even want to do that. 2, that's weird. So if you try and use an invalid function, sometimes it just throws up this error saying you haven't defined a proper function. But this should, there we go. So this should work. So, you know, if we sum the rows or the columns, this is what we would get. If we sum the rows, right, we get a
And it
different
could be
result.
both, if you like them separately.
I'm not sure. I don't,
No.
it basically just reprints the data frame because it's taking the sum of every
Oh, okay.
individual,
Yeah,
every individual cell.
okay.
It's, you would do that, like
I was
if you,
just curious.
if you had like a matrix of like summary statistics, then that might be an application for that. In practice, I've never declared both rows and columns. So that's apply. Again, like the apply, like my recommendation is start programming for loops and then transition over to writing the appropriate apply. And almost always you're going to be using like either lapply or sapply. That's just sort of what I find. So, because yeah, any like the vanilla apply has basically been superseded by tidyverse functions. So, okay, so functions. I know we don't have a ton of time left, but again, this just allows you to make a general version of a command and use it in different circumstances, right? So remember, we had this recode statement. It's like, well, we can generalize this by creating a generic function, right? So the function, we define a function and we declare our variables inside the function. And then we define the function following it. And then we output the function to some object, right? So in this case, the function is called make Likert. And it takes one argument, which I've defined as X.
So why do you have to have the ...
You don't always. And so the ... is like, it says it will pass through any additional commands that you put within your function call
Okay.
over to the output. And I've just gotten used to anytime I write a function, I just add the ... In this case, it doesn't.
Basically have additional.
Yeah.
Like function commands in your.
Right.
Yeah.
Where it's because R does something called lazy evaluation, where it only evaluates an argument if it has a need to evaluate it. So if you say, if I were to call the make Likert function, which actually let's run this, and then I'll show you what it does. Right, so now we have this command called make Likert, right? Like I could literally write make Likert like cat equals Bob. And it still runs because it's like, well, the function doesn't have any place where there's an argument called cat that takes a string input. So it only evaluates an argument if it needs to. Where the ... is useful is like, let's say you're writing a wrapper function for like a ggplot command. You don't always want to put like scale x continuous, but you might want the ability to add extra commands that are necessary. And so that's where you would use the ... And it just means like everything inside the function call. And a function call is literally just this, right? So I'm calling the make Likert function. It just says any other arguments you see there pass through the function.
Can you call a function from a different package?
Yeah. So like if you use the mass function, so when you like start running like ordered logit models, and if you load mass before dplyr, and then you try and select things, you're going to get an error because mass has its own select function. And so if you want to override something, you just have to write the name of the package, right? So like dplyr select. And then, yeah, so the name of the package, double colon, and then the name. And you see now it's knowing that we're going to do the dplyr version as opposed to if I wanted the mass version, select. Anyway, so yeah, so this is a make Likert function. It's a function that I've actually made, and that I often use. And so see here, it's done the same thing, right? And we can check it's outputting the same values, right? Now, what gets really cool is it's just again more comparisons. We can, call the function and assign it to a new object, right? So this is creating a data set dat3, and yeah, we're just running the make Likert command for each variable to do, an expedited recode. But why would we do that when we can just apply the function we created in the same way we did before, right? And so that's literally what this piece of code is doing, right? It's just like I defined the function. Now I'm going to make this apply loop, and I'm going to apply over, from 1 to however many number of columns dat2 has, the function below, and the function is run the make Likert function, right? It's just a single function call. And then from here, if I do, this is cool1, you see that's the entire variable there, and I can go like table, this is cool1, and it'll give me the univariate frequency distribution, right? So that's pretty cool. A more complex function. So here this is just making a categorical variable because I'm going to do some crosstabs. So if we wanted to calculate a crosstab, right, we could use the table command and then pass it through into a proportion command and say, find me column proportion, since that's what we usually work with in the social sciences. And we have our crosstab with column percentages. This is if you want to learn how to do it using tidyverse. But that's really just a jumping off point to this crosstab function or graph crosstab function that I wrote, where it's like, okay, so we did this, calculate the crosstab thing, and then let's also create, we'll create one instance of graphing this crosstab. So there you go, you have our V1 cross-tabulated against categories of something, and then we calculate the column proportions. Just random tip, if you want to know that you've got the right column proportions, i.e. they're summing to 1, use geom bar because it doesn't force it to fill to 1, which would be the geom fill command. So just a little tidbit there to check. So yeah, so let's chain those two things before, that I wrote before, right? So here I defined a function. I'm going to call it ggplot xtab, and the function takes 2 arguments, a data frame and then the variable name. And this is all the function's doing, right? So we take our data frame, and then we calculate a bunch of summary statistics to it, and then we pass it through to a ggplot command, and that creates our graph, right? So if we make this, we can run this function, and it's created our crosstab, right? And so I just saw that this is not good. Symbol. Like if I try this with V2, I don't think it's going to work. Yeah, it just keeps saying V1 here. So oh no, that's why I didn't. Yeah, because the way the dplyr syntax works, it always calls it V1. So this will still work for like V2. Let's just check this here. 3. Oh no, it actually still was doing V1. So okay, I'll diagnose that and put a correct version of the function that actually works. But you get the idea, right? Okay, I know that was a very quick introduction to functions, but it's sort of difficult because unless you know what you want to do, it's like, I mean, I could come up with functions until the cow comes home, but like whether that's useful to you is another thing. So my first big function that I wrote, and this is literally the script file that I wrote. I wrote my own summary statistics function, right? So I called it describe, and it's just, yeah, like give me the frequency distribution, the proportions, the marginal percentages, and then a bunch of summary statistics, right? So give me the mode. So name, what type of variable is it? If it's categorical, give us the modal stuff, calculate, mean, standard deviation, variance, total N, valid, total NAs, give me, yeah, mean, SD, variance, minimum, median, maximum range, valid N, right? Confidence interval of the mean, 95% confidence interval bounds. Because yeah, it was just a practice in writing a function. So that's.
So how did you go from whatever you were doing before to that? Like, is that because you were always making? So you, for that function, like you started with just like an empty data set and then built it by putting all these things in, basically.
Yeah. Yeah. I've been working on this for a while, and I recently revisited it. Don't tell Mathieu that, because I should be working on a proposal. No, it's not this. Because I know several of you are helping Dr. Stevenson out with some CES reports. I've actually been building this suite of crosstab functions. So here it like makes a crosstab out of a data frame, makes omnibus crosstabs. So one dependent variable against many independent variables, and then does a bunch of graphs to it. So, this might be a reading break project or something that I do after I finish my proposal. But this, I'll put it up on GitHub, and then it might make your guys' lives easier, because this is something that I started writing to help me with my private sector work. So yeah, so that's where like, you know, the functions I wrote came from was because like I'm doing this thing all the time
Yeah.
and I don't want to keep retyping code. So yeah, you know.
Is it possible to put like automatic checks with the function so you can give a custom error? for your mistakes?
Yes, and you should if you're writing a package, but almost always that is probably a waste of time for you. Because you should like, you will have spent enough time on it that you should know what it's doing.
I don't know. It's more for other people.
Yeah.
right?
And our messages can get weird depending on the kind of error it runs into. And so you need to learn how to like open up the traceback of function calls and see like, well, where did things go wrong? And then as you build more and more advanced functions, what you'll end up doing is, you know, let's say you decide to add another command at the end of it and it breaks the function, right? So what you should do is comment out everything after that point where it gets broken and then output something else and then run the function, look at the output and see like, is this outputting what it should be? And that's sort of how you do the troubleshooting. And that's, yeah, so in the function definition, you'll see that one thing I have is return. And if you're going to create an object, this should always be the last. Like sometimes it's redundant. Like I could have just put X, which anytime you put just the object, R assumes you're telling it to print that object. And that often will suffice, but more formally, you should say return this, right? And I'll show you the back end to the survey effects function, that package that Dave and I wrote. Like this isn't even a function. This is a method, which is one particular dispatch of a function. And there's, you know, over 500 lines of code. And then there's a bunch of conditions, right? But the output here is a list. And so you'll see, you know, this function outputs a list with an object called predictions or preds, an object called seed, an object called sims, and an object called formula, right? You know, and then I return this object called output as whatever the function spits out, right? So it's a good practice to say at the end, return something. So again, like functions, you kind of just need to play with it and write stuff, you know, so start with something that you find yourself always doing, but not necessarily in an iterated kind of way, and then write a function to it. And even if it is something that you're doing in an iterated kind of way, write the function, so then writing the loop becomes easier. Yeah. So any questions about functions? I have a little 5-minute blurb on looping models, but we can keep talking about functions for a bit here. Any questions in Zoom land? No. Okay. So the last thing I'm going to show is using loops or apply. Like loops are a general thing. Like an apply is actually a loop because that's basically how it works. Though implicitly when we say loop, we mean for loop. Because if we want a while loop, we'll say while loop. Anyway, but looping and applying functions is useful when we're running models because we very rarely run one model. And when you're tweaking models, it's like, you know, do you want this version of this latent variable or do you want that version of this latent variable? And if you're running 4 models, it's like, fuck, I got to go to 4 different places to get it done, right? But by using loops, what you can do is you can make running multiple models easier. This gets really handy, you know, for something like voting behavior. Like if you're doing the block recursive model, it's like, you know, you're running like 6 models, but each model is really just an extension of the previous one, right? So it's like, well, why, you know, well, let's say you want to change what which version of your education variable you're using or region, right? It's like, well, why would you change that in so many different places when you can just change it in one place, right? So here I have this, this is a practice data set of the 2019 CES right here, and I'm modeling feeling thermometer ratings of the three major parties, right? And I modeled it as a function of gender, age, region, education, and our data set is CES. And again, if you look at this, it's like, well, why the hell would we do it this way when we can see that the only thing that changes is the DV, right? So yeah, we could run it like this, but that's a bit laborious. So what I did here was, well, I'm going to make a vector called my DVs that has just the name of the dependent variables I'm going to use. I'm going to create a vector called my forms, right? So my formulas. And oh, look, those are the model formulas for each of the models that I want to run. And then I'm going to create an object called my models, to which I'm going to apply from 1 over the length of my forms, the following function with the variable I. Run lm with the formula of my forms of the ith sub-object of the object my forms over the data set CES. Right. And so now if I run this, oh look, it's all there. Yeah.
Go over it again.
Sorry, you go over
Just,
like how to read the
yeah.
So list apply from 1 over the length of the object my forms, the following function with the variable I. LM command, where the formula equals the ith slot of my forms. I shouldn't call it sub-object because it's slot is every item in the list is a slot. So the formula equals the ith slot of this vector my forms. And the data is the CES data set, right? And Stargazer is great. And even the new package model summary, both model summary and Stargazer take as an input lists. And so it's sort of set up for you to have all of your models in a list because that's how it's set up to take it
That's
anyway.
super handy.
So yeah, I mean, could you imagine like,
Yeah.
you know,
because usually you have so many like model outputs if you're showing a paper or something.
right.
You could just put them all in one.
Yeah.
Easier.
And then especially like, if you're gonna, like, let's say this was some like, 4 binary variables, right? And then you have for each of your 4 binary models, you have a 3-stage model. And so like that's 4 times 3, right? And that's just running the models. Then you have to calculate marginal effects. Right? And so if you have, let's say your stages are like 4, 5, and 6. So that's what 4, 6 is 10 plus 5 is 15 for the last one. And then the second one is 9. The first one is 4. So 9 plus, so 4 plus 9 is 13 plus 15 is 28. It starts to add up. So
Sorry, I had to run.
No,
but
it's all
this
good.
was great.
Yeah.
Thank you.
you're welcome. So yeah. So yeah, so this is one really great place. And I mean, I whipped this up together quick. Like, what you could do is actually, you could like have like a stage 1 template, a stage 2 template, and a stage 3 template, and then using the paste command, sort of assemble combined formulas together, which then you would have to coerce into a formula object using the command as formula. But it's, it seems complex because you're like, well, didn't I just write the same number of lines as I did before? But the fact that here it's like, well, I can go to one place and change everything. I think that's easier, right? So, if you, like, let's say you didn't want to keep writing this out, right? So you could go DVs. So let's, like my IVs, where it's just a text string, right? And then under my forms, you could go so to combine these into a formula, you could use like the paste function, right? Of my DVs 1, and then paste that with the tilde, and then paste after that my IVs again 1, right? That looks like a formula, doesn't it? So then now you can just, how would we turn this into, like, how would we loop this? Right, so we could do L apply 1 over length, we'll call this like my forms. Well, I've just overwritten it, so length of my forms. Oh, shoot, yeah, no, that's not what, right, because I'm iterating this. So 1 over length, my IVs, and then curly braces, and then we'll define the function variable I, and then the function is simply paste. It's I, it's I. DVs, sorry. Oh. DVs, yeah. So over the 1 to length of my DVs, function I paste. Oh, my IVs is always the same. So that's why I didn't need to do that, right? And then now I have all of those things, right? Yeah, and then you could output this to my forms instead of this. And then now, like, okay, well, maybe I don't want education as a factor variable. I just want it as a binary. My has uni. I think that's what it's called. Let me just see what it's called. Names, CES. Univ. It's just univ. Why is this not working? Oh, as dot formula. That should work. Just change this to religion. Yeah, there you go, right? Makes it super easy, right? If you wanted to add the left right variable to here as well, well, then let's go left right, my forms. Now it's been added there, right? If you wanted to go block recursive, right? My IVs, you could go, maybe this is block 1. Maybe, actually, let's do, maybe this is block 1, and then maybe block 2 just has religion plus left right. We could do, you could nest this, right? So my forms is 1, and then my forms 2 is, this is 1, this is 2. And then you could do like all forms is just unlist my forms 1. C unlist my forms 1 unlist my forms 2. Yeah, and now these are why is it not? Because I need to add. Aha. And then if we look at just this, there, now we have the stages, and then we can simply run all models. All forms. Come on. Right, all forms.
John?
Yeah.
Put all of them into like this, and this layout of 1, 2, 3, 4. Is that a Stargazer thing, or how do you get that?
Yeah, that's just a Stargazer thing.
Oh, okay, so
Yeah.
how do you specify that in Stargazer?
So
People?
that's just the default,
Oh,
right? Like
okay.
it takes as an input a list.
Okay, so if you have multiple models, it just says that.
Yeah.
Okay, that's good.
So, right, I mean, like that's way faster than typing in 6 different formulas, which then you might have to change 6 different times. And
Yeah.
because yeah, this is the same thing as writing like Stargazer, like my models like 1, my models 2, right? So if I just wanted like the first stage, you know, I could do this and it would just give me the first 3 stages, right? So anyway, yeah, like this is, it took me until getting to the PhD to learn how to, you know, midway through the PhD to sort of figure out the power of scripting stuff. But it's like, if you can figure it out, it's a powerful tool. So anyway, we've already run 15 minutes over, so I'm going to leave it there. I'll fix the code for the crosstab function. And then whenever I finish writing that R package and put it up on GitHub, I'll send an email out to the folks who attended. But are there, like, do you guys have any questions, or anyone in Zoom land have questions? No. Okay, well, that's all she wrote, folks. Thanks for coming out. Good to see you drop in, Max. I got to run, otherwise I'd chat with you, but always nice to see your name pop up on a screen. So
yeah, thanks very much, John, for organizing this, and good to see you too.
yeah, sounds good. We'll catch up sometime.
Okay, bye.
Okay, yeah, thanks for coming out. Thanks, Hugo.